Well, let's continue. Here we have an example. Okay, let's read. An AM radio station transmits at 1 megahertz.
Siz zapisi bosmadingizmi uncha?
I have started the recording. Yes, I have started. Okay, at some distance from the antenna, the amplitude of electric field intensity is 10 volts per meter. The wave propagates from the station outward uniformly in all directions, and the electric field intensity is everywhere perpendicular to the direction of propagation. Okay. Assume air has the properties of free space. Okay, first question is find magnetic field intensity of the wave. First of all, what we do? We know, first of all, we know that frequency is 1 megahertz, 10 to 6 hertz. And at some point, at some distance from antenna, the electric magnitude of electric field intensity is 10 volt per meter. Okay, 10 volt per meter. Well, one moment. Okay. The magnitude of electric field intensity is 10 volt per meter. So, how do we solve? First of all, because of the fact that transmission is uniform, propagation is on a spherical surface to all directions. At large distances from the source, at very large distances from the source, the spherical surface may be viewed as a plane. So here we have a source and we have the transmission of radio wave. At some very large distances, this spherical surface can be seen as a plane, and therefore transmission may be approximated as a plane wave. Okay, we may approximate it as a plane wave. Assuming that the vertical direction coincides with the z direction, we may write electric field intensity as z directed and propagating in the x direction parallel to the earth. Okay, so from the we assume that vertical direction as z and direction of propagation of the wave x. So the wave propagates in the x direction, which is parallel to the earth. And electric field intensity now the electric field intensity varies with x. Therefore, the electric field intensity we may write as Z E Z, or not EZ, we may write directly E0 multiplied e to the power of minus j kx. Or in our case, we may put also k0 k0 as well, because the k0 is the intrinsic impedance of free space. So, okay, volt per meter. Now, from the Faraday's law or from Maxwell's equations, we know that rotor of electric field is equal to minus j omega mu 0 h. Yep. Rotor of electric field, as we have written before, is x dEz over dy minus dEy over dz plus y dEx over dz minus dEz over dx, and plus z dEy over dx minus dEx over dy. Okay. So everything will be equal to minus j omega mu 0 x hx plus y hy plus z hz. Okay, as we have done in previous lesson, let's see. We have only a z component of electric field intensity, which varies along x, or in other words, I may write here E z along x is not equal 0, and Ey and Ex are 0. So, okay, it means if we look here, Ez dy, Ez varies with x, and with respect to y is constant. That's why it is 0. Ey is 0. Ex over dz, this is not 0. Ez over dx, this is 0. Ey is 0. Ex is 0. That's why we don't have x component, we don't have a z component. And again, what we have? We have dEx over dz. dEx over dz is equal minus j omega mu 0 minus j omega mu 0 no, sorry, I have done a very bad mistake. Okay, look here, Ex is 0 and here, sorry, this is not 0, or dEz over dx is not 0. That's why we have dEz over dx, which is equal to minus j omega mu 0 hy. So what we have? We have dEz over dx is equal to minus j omega mu 0 hy. And from here, hy, so from here, hy is equal to 1 over omega mu 0 multiplied, not 1 but j, sorry, j over omega mu 0 multiplied by dEz over dx. Now we found h in terms of Ez. Now we need, in order to find the final expression for h, we need to compute this derivative. So in order to compute this derivative, what we need to do? So dEz z component along z is equal to this expression. And okay, let's go to our last page, and dz and Ez was E0 e to the power of minus j k x, or k0, of course, k0 x. Yes, and if we take the derivative, we have minus j k0 minus j k0 e0 e to the power of minus j k0 x, or we know that this term is equal to the ez of x, and we have minus j k0 ez of x. And for hy, we have j multiplied by j is minus 1, minus minus simplifies. We have k0 over omega mu 0 multiplied by ez x. So this is the y component of magnetic field intensity, or we may write it in vector form. So okay, hy, let me write hy, we said, is equal to k0 over omega mu 0, k0 over omega mu 0 ezx ez of x. So k is equal omega multiplied square root of mu 0 epsilon 0. So we have square root of epsilon 0 over mu 0 ez of x, and this expression is 1 over eta 0 1 over eta 0, and it means, so so 1 over eta 0, or ezx over eta 0. And what about ez? Ez was hy is equal, ez was equal to e0 multiplied e minus j k0x. e0 multiplied e minus j e0 e to the power of minus j kx over eta 0, or in terms of vectors, h of x will be equal to y multiplied e0 multiplied e to the power of minus j kx over eta 0. Yes, this is the magnetic field intensity. Okay, the next question of the same problem. Okay. The next question of the same problem. Write the electric and magnetic field intensities in the time domain. Well, B. We need to write electric field intensity in the time domain and also magnetic field intensity in time domain. If you notice, if you pay attention here, we've written in the form of phasors, in the form of phasors. This is also in the form of phasor. Now we need to write in the time domain. Do you have any idea how to write electric field intensities and magnetic field intensities in time domain? Do you have any idea how to write?
O'sha formulasi bor ustoz.
Okay, which formula?
Kecha yozdik-ku, o'sha masalan electric field epsilon 0 cosinus o'z ichidan omega t minus phi z mi? Ana shunaqa formulasi bor-ku, o'shanga qo'yib qo'yaylik.
Okay. You are
Kan o'rniga qo'yib.
Yeah, you are speaking about this formula, I think, is equal the real part of, so the real part of yes, real part of, in our case, electric field is E0 e to the power of minus j k0 x e j omega t, and it is only in z direction. So what will be the result? The result will be E0 or, okay, let me write first unit vector z, E0 of real part is associated with cosine omega t minus k0x. So in our case, E0 amplitude is 10. What about omega? Omega is 2pf, and 2pf is 2 multiplied p multiplied, the frequency was 1 megahertz, 10 to 6. Okay, you know how to compute k0. You compute and you write the numeric values for electric field intensity. Electric field intensity will be equal to Z multiplied by 10 multiplied by cosine 2p 10 to the 6 t minus k0x volts per meter. And what about H? H is simply E0 by eta 0 and in y direction. So, okay. H is in y direction. Okay, we know eta 0 was 377 ohm. So H is 10 divided by 10 divided by 377. Okay, 10 divided by 377 is 0.0265. 0.0265 multiplied, the rest is the same, 2p 10 to 6 t minus k0x ampere per meter. Okay, this part of the problem is also done. Now we have third part of the problem. Look here, sorry. During very heavy rain, the effective relative permittivity for air changes from ER1 to ER1.5. Calculate change in phase velocity, intrinsic impedance, and magnetic field intensity, assuming that amplitude of the electric field intensity remains the same. Okay, can you do this part of the problem by yourself? Can you try?